everyone is having a nice day and is ready to be part of the second day of the 7th International Conference on Recent Advancements in Composite Materials, ICRACM 2024, hosted by the Institute of Science and Technology at Chinmaya Vishwavidyapeeth, deemed to be University, Kerala. First of all, on behalf of the university and the organizing team, we thank everyone who have registered and have joined for listening to the keynote speeches, presenting their papers, and also participating to learn more from the conference. Your support and encouragement means a lot for the organizing and also for the success of the conference. Let's start the day with the blessing of the Almighty with a prayer. I invite Dr. Prabhavati ji, Assistant Professor in the School of Kala Yoga at Chinmaya Vishwavidyapeeth, deemed to be University, for the prayer. Praveen sir, is she not available?
Yes. I think we can start with Nivedita.
Yes.
Yeah.
Sahana bhavatu sahanau punaktu sahaviryam karavavahai tejasvinavaditamastu ma vidvishavahai. Om Shanti 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 Hari Om. Shri Gurubhyo Namaha. Hari Om.
Thank you, Nivedita. She is a second year student of BTech Computer Science at Chinmaya Vishwavidyapeeth. Thank you, Nivedita. We all are waiting to listen to the keynote speech by the 5th keynote speaker of the conference. I invite Dr. Rashmi NG, Senior Assistant Professor of Computer Science in the Institute of Science and Technology, Chinmaya Vishwavidyapeeth, to introduce the speaker.
Good evening, everyone.
Rashmi ma'am, you are not audible.
No.
Audible now?
Yes, you are audible.
Yes,
Hey everyone, and a warm welcome to the keynote session 5 of the International Conference on Recent Advances in Composite Materials 2024, organized by Chinmaya Vishwavidyapeeth, deemed to be University. We are delighted to have such an enthusiastic and diverse group of participants for this event. Before we begin, I would like to share a few pointers to ensure the smooth functioning of this session. Please keep your mic muted during the presentation to avoid any interruptions. We encourage you to actively listen and take notes of your questions during the session. Meantime, You can type your questions in the chat box for the speaker to address them. Let us all maintain decorum by refraining from interrupting the speaker during the talk. Now, it's my privilege to welcome Sorensen Professor in the School of Engineering and co-director of the Mechanics of Undersea Science and Engineering Center, Brown University, USA. His research interests are in computational science and engineering, with emphasis on modeling and simulation in solids and structures, fluids, and their coupling in high-performance computing environments. For his research contributions, Professor Yuri received many awards and honors, including the 2018 Walter E. Huber Research Prize from the ASCE, the 2020 Gustus L. Larson Award from the ASME, and the Computational Mechanics Award from the International Association for Computational Mechanics, ICRACM. He is included in the list of highly cited researchers, both in the engineering and computer science categories. Yuri recently completed his service as the president of the U.S. Association for Computational Mechanics and as the chairman of the Applied Mechanics Division of the ASME. He currently serves on the U.S. National Committee for Theoretical and Applied Mechanics. Today, Professor Yuri will share his insights on isometric geometric analysis, breakthroughs in computational mechanics of laminated composites, and beyond. Please join me in giving a warm welcome to Professor Yuri Bazilevs. Welcome you, Professor, and over to you.
Thank you very much. Thank you very much, Resmi. I just need to minimize your window, and I think we're ready to go. Okay, well, thank you very much for this invitation, the organizers of the meeting, and especially VGI. We actually know each other also socially because VJ's daughter is my neighbor here in Massachusetts. So it's a very lucky coincidence that I'm here, and I'm happy to tell you more about our research. Okay, so I'll be talking about IST geometric analysis, and specifically as it applies to the computational mechanics of laminated composites and some other examples. Okay. So let me start with a slide here, which shows the use of composite materials in aviation. Okay, you're looking at the graphic that on the abscissa shows the year, and the ordinate axis % of structural weight of a given aircraft. Okay, and if you look in around 2010, 2014, 2015. You see that famous models like Boeing 787 and Airbus 350 are at this point over 50% of CFRP by weight. Okay, so what's so special about composites? Of course, we all know about the low weight and high stiffness, very attractive properties in aviation, and strength.
Professor?
Yes.
Have you shared the slides?
Yes.
No, it's not here. It is not coming here.
And let me see. Maybe I should share again. Here we go. Okay, this is better.
Yes, it is coming. Yeah, you can go.
Okay, great. Okay, so let me go back to this graphic, right? And it's really just to motivate the fact that at this point, over 50% of structural weight of aircraft like a Boeing 787 or Airbus 350 are CFRPs. Okay, so what's so attractive? Of course, we're looking at the low weight, high stiffness ratio, and strength. Intentional though, right? In compression, the behavior is a lot more complicated. So what it does, right? Composite aircraft, you get a lighter aircraft, resulting in cost savings, as when it comes to, let's say, fuel use. Another benefit that people really appreciate, that you can have higher cabin pressure, right, leading to improved passenger comfort. Okay. However, compressive strength after damage is poorly understood, And as a result, damage detection becomes more complex than in, let's say, metal, aluminum structures, aircraft. And the certification process itself is harder, more tedious, and costly, okay? And so it does create a need for advanced modeling and simulation for this class of problems. When we look at CFRPs, as we all know, they undergo complex response for various loading cases. Intralaminar damage due to fiber breaking and kinking, matrix cracking, interlaminar damage or delamination due to debonding between the laminate plies, right? And another aspect that's perhaps not so appreciated is you have the development of permanent deformations, okay? Kind of a plastic-like response, even under low velocity impact. And so if you look at things like compressive strength, okay, it's reduced not only due to the interlaminar damage or delamination that occurs during, impact type events, right? But also due to permanent deformations that act as geometric imperfections to which thin structures are highly sensitive. So all of this creates a need for an advanced multi-layer theory which can account for these effects, okay? And the corresponding numerical formulation that's accurate and efficient. So if we focus on the state of the art, right? Typically, a given structure is or a laminate is broken up into the different lamina. They're connected by cohesive interfaces, right? And oftentimes, to save costs, you do things like ply grouping. Okay? When it comes to computational approaches, what's prevalent today is the use of finite element methods that either use linear hexes, and I'm using here the notation of abacus type elements, or solid-like shells on each ply, okay? But if you carefully look at this technology, you see that these are susceptible to what's called transverse shear locking, especially in the thin shell limit, right? Where each ply becomes very thin, okay? You get fairly inaccurate stresses due to lower order approximation that's involved, right? These are only piecewise linear finite elements, so you get stresses that are only constant on each individual element, okay? In explicit calculations, which are often done for impact events, you get small time step sizes, right? Coming from stable time step restrictions because of high stiffness and low mass, okay? And also, when you start looking at sort of curved structures, you need high element count just to represent the curved geometry, okay, and resolve the stresses in these regions. And so, even if you want to do an impact on a coupon, consisting of 8 to 16, perhaps 24 plies, right? You're looking at meshes that are on the order of 500,000 to 1 million nodes. Right, imagine 3 displacement degrees of freedom of at each node, and you're looking at something that's 3 million for a simple coupon just to get things right. And so, of course, some innovation is needed. Okay, and this is what I'd like to talk about today. So what you're seeing in this picture, right, what is an application in computer graphics, architecture, computer-aided design. And what sort of unites all these pictures is the use of highly efficient, smooth spline technologies, B-splines, or you see here NURBS, non-uniform rational B-splines. And so it seems like this technology is everywhere, but in computational mechanics. And so this is something that we proposed a few years ago, Professor Hughes and another colleague at the University of Texas. The first paper appeared in the fall of 2005. And the underlying technologies is based on, technologies like NURBS, T-splines coming from computational geometry. And so what we call the resulting modeling methodologies, isogeometric analysis, coming from the word Greek, iso-1 geometry, okay? So what do we mean, right? We take the objects that are represented like this, okay, in CAD systems using splines, and we're using the exact same spline functions to represent solutions over these objects, okay? For things like displacement fields, temperature fields, and so forth. So one way to think about isogeometric analysis is you have sort of exact geometry as defined by your CAD system, okay, where you design these objects, and in combination with the isoparametric concept of FEM, meaning you're going to use the same functional description for geometry and for the solution field that's designed over that geometry. Isogeometric analysis includes standard finite elements as a special case, but it offers some exciting possibilities, such as precise and efficient geometry modeling, okay, simplified mesh refinement, very nice approximation properties, basis functions or approximations that are smooth between the elements, and we're going to take advantage of that. And then the community works towards the goal of integrating design and analysis. Okay, so let me illustrate things in a simple example. Supposedly you have an elastic bar which you want to discretize using 3 elements, linear FEM, right? And so one way to show how the displacement over that bar distributes, right, is by plotting the basis functions associated to each one of these nodes, right? And so you're going to have a piecewise distribution of the displacement, which gives you constant distribution of the strains and constant stresses. Okay? And so if you want to know how your error behaves when you refine the mesh, your stresses will converge at order h, right, where h is the element size. And then your displacements will converge at order h, maybe a little bit slow. Okay. So one way to increase the accuracy of your analysis is to go from linear to, say, a quadratic representation, right? Where again, you can keep the same 3 elements. You have C0 continuity of your functions between the elements, and you complete to quadratics, right? But there is another way to go higher order, right? Is again, you get fully, you're complete to quadratics on each individual element, right? But rather than using C0 approach, right, you make them C1 continuous, which you can make in the quadratic case, right? And so now if you compare the number of functions in the quadratic case, here you have 7, right? For FEM and for splines or for NURBS, you have 5, right? So you save quite a bit, right? And then imagine if you go into 2 dimensions or 3 dimensions, the savings become significant, while at the same time you're maintaining the accuracy that you like because you're still complete to higher polynomial order than linear. Okay? Now, what you also can do, you can bring in objects, okay? All the conical sections like circles, cylinders, and so forth, right? And for example, it takes 3 nodes, right, or 3 what we call control points to represent a piece of a circular arc of an arbitrary angle, for example, right? And if you want a complete circle, all you need is 8 nodes to represent a circle, right? Imagine how many linear elements you would need to get the same type of accuracy, right, in geometry representation. So I think there's some benefits to be had in computational analysis, right? So now when you think of CAD, right, there's a lot of very well-developed surface technology. Okay? You can very quickly build complicated surfaces. And as a result, when it comes to sort of advances in computational mechanics, as you can imagine, while isogeometric analysis has impacted many different areas, solids and fluids and electromagnetics, so forth, right? There's been quite a bit of new work, I would even say a renaissance that's occurring in the field of shells. And this is what I'd like to take advantage of for composite materials applications. Okay? So let me take you briefly through some of our recent work on Kirchhoff shells, okay, which forms the basis of what I'll show you later. Okay, and here we imagine structures that are much thinner in 1 dimension than in the remaining 2. Okay, and so representation of such a structure can be obtained as follows. Right, you get a structural mid-surface, which is given here. Right, and then you take the mid-surface, you parametrize the mid-surface. Okay, and then you extend it in the thickness direction by h, okay, halfway up and then halfway down, right, in the direction of the normal, right? And then that normal you go and you compute directly from the representation of your surface. So the entire 3-dimensional object, the parametrization, okay, makes use only of the parametrization of the mid-surface and the positions vector on the mid-surface. You can think of this as a parametrization, but you can also think of this as a current configuration of your structure, okay, as it moves through space during a deformation process. Okay, so now that you have that description, okay, right, you can think of mechanical analysis, right? You can think of computing stresses, for example, from a given constitutive relationship, right? And there, you can, let's say, use the measure of deformation. You use a strain rate, okay? How do you compute a strain rate? You need to take a velocity field, right? Take its gradient, right, with respect to current position, right? And symmetrize it, right? When you look at the definition of the spatial velocity gradient, which is given here, right, you can decompose it in 2 parts, right? You apply product rule. It's a parametric gradient of the velocity multiplied by the inverse of the parametric gradient of the position, right? And so this is where you hook up with the Kirchhoff shell, is that you use exactly the expression derived in the previous slide, right, to get the parametric gradient of the position, right? So you can expand it here. you end up getting a parametric gradient of the mid-surface, right? You need to differentiate through the normal vector, okay? And the normal vector is defined here, so you start looking at second derivatives now, right? This is sort of a price to pay. You can't use traditional finite elements, but you need to be able to use functions that do have second derivatives, like splines, okay? Then you can develop a velocity vector by taking a Lagrangian time derivative of the position, right? And again, you have the velocity of the mid-surface and the rate of change of the normal. Once you have the expression for the velocity, you can develop its parametric gradients, and now you have a complete description of the strain rate, which is consistent with the Kirchhoff-Love shell theory. Okay? And so the rest of the formulation looks like what you would do in traditional finite elements. You use a principle of virtual work, principle of virtual power. These are the acceleration terms. These are the stress terms. These are the body forces, surface tractions. Okay, right. And so then for your accelerations, for your virtual velocities or the test functions, again, you employ the expressions that are consistent with the Kirchhoff-Love theory. Okay, so it's really a full three-dimensional solid formulation where the kinematics is restricted to Kirchhoff shells, right? And now you go from the continuous to the discrete by using your spline functions like B-splines, NURBS, or some of the unstructured variants like T-splines. You parameterize the mid-surface in the current configuration. You compute the velocity, and then you take these expressions and introduce them into your weak form that you developed here. You end up with a standard Galerkin approach of finite elements, right, where you recognize the acceleration terms, body forces, surface tractions, right, and sort of nodal forces that are coming from the internal stress terms. Sigma here is the Cauchy stress, and B is this velocity gradient or the strain displacement matrix that you see in traditional finite elements, but which is again consistent with the Kirchhoff-Love theory. Okay? And if you look at this slide, the expression for the strain displacement matrix looks absolutely unpalatable, but you derive it once and for all, you program it, and you have a method. Okay? So let's see how this works. We're going to take a square tube. We're going to crush it. Okay. And you see that it collapses in the accordion mode. Most of the plasticity occurs right at the at where the at this edge here, at the right angle. Right, and you can see that the accordion mode is similar to what you see in the experiments. Right. This is another problem we did. We took a soda can. We measured it. It's very thin, right? The thickness of this thing is a fraction of a millimeter. Problems like this drive commercial solvers crazy, and we're gonna crush it and twist it at the same time at a very high rate. Okay. And so here's the response. You see immediately formation of the plastic zones. This is effective plastic strain, right? You can actually see the formation of these plastic buckles, right, in these very sharp corners. And then you can continue the calculation for very, very large strains, and the calculations don't blow up, okay? So this is the kind of robustness and accuracy that you can get out of doing these problems using spline-like discretizations as opposed to traditional finite elements, okay? And what I'm showing you here, these are not my results, these are results from a paper by Kendrick Shepard, presented at the SIAM International Meshing Roundtable in 2023, where isogeometric spline technology was used to carry out a car crash analysis of the body in white of the 1996 Dodge Neon. So this technology is making its way into commercial software like LS-DYNA, and is really of great interest to the automotive industry. Okay, so now let me move on to the composites part, right? And so what we did here, we essentially we took the formulation, right, for the shell, and what we'd like to do now, okay, is kind of extend it to a multi-layer theory. Okay, so the goal here is to represent multiple layers of the laminate, right, and account for the most common failure modes of laminated composites. Okay. And we'd also like to develop a framework that's an alternative to finite elements that is more accurate per degree of freedom, more efficient, and thus can take you from sort of coupon level simulations to at least being able to handle structural components. And so the idea is to use the Kirchhoff-Love to represent individual plies, right, or ply groups, right? And then these structures, the individual plies are truly thin. There is really no need to introduce transverse shear strains, right? There's no transverse shear stresses. We feel like isogeometric methods are perfectly suited for this application because, you know, the definition of structural surfaces, again, can be obtained directly from CAD, okay? You get the computational efficiency, right? Because you only get displacement degrees of freedom on each individual ply, okay? No rotational degrees of freedom, right? No possibility of transverse shear locking because there is no transverse shear. You get geometric exactness on the coarse mesh and a natural integration with the CAD systems. For the damage modeling part, we're not doing anything particularly new. We're just using traditional continuum damage mechanics, representing fiber, matrix, and shear damage, machine criteria for damage initiation, bilinear damage evolution law for each mode, and the length scale is brought in through the crack band model of Denek-Bazant. Okay. To simulate the delamination, we take our Kirchhoff shells, right? And these are deformed, you know, they deformed individually, okay? They don't know anything about each other. And we connect them through cohesive interfaces, okay? But these cohesive interfaces can fail, essentially enabling us to simulate delamination. Okay? And in particular, we're developed a mixed mode cohesive model where we take two independent opening modes, but a single damage variable representing delamination. Okay. So again, let me take us through some of the modeling details, some of which are, you know, fairly traditional and some of which are new. Okay. So first, we you know, to model plasticity, okay, we work with the effective Cauchy stress in the corotational system, okay? The corotational system involves the use of a rotation matrix here. The rotation matrix is associated with a polar decomposition of the deformation gradient, right? Which means that it will rotate with the material axis. And the key is that it's initialized using principal material axis. So at every integration point or at every material point, wherever I need the stress, okay, the rotation matrix is initialized, you know, pointing in the direction of fiber and matrix and through thickness direction, like this, right? And then it's advanced in time, you know, using an appropriate algorithm. So with this technique, you get incremental objectivity for large deformations and anisotropy at the same time, right? And so now in this principal coordinate system, we define a corotational strain rate, right? We use the rate form of this of the stress equation, right? dP is the plastic strain and the corotational coordinates. Here's a definition of a yield surface. It uses a plastic potential that's expressed in this sort of matrix format, right? P is the projection tensor, where you can clearly see that we're only taking into account stresses in the matrix direction, okay, and shears, right? So we're assuming that no plasticity occurs in the direction of the fiber, and we use power law hardening, which is again common for epoxy type materials, right? And on top of that, we're applying continuum damage mechanics. This is the damage operator, right? We use, as I mentioned, Hashin's criteria for damage initiation, right? We have 4 modes: compressive and tensile fiber failure function, and tensile and compressive matrix failure function. Like, we track the modes individually using bilinear law, linear softening here, okay? Then we convert the damage indices into the damage variables associated with fiber, matrix, and shear. And we use a little bit of viscous regularization to sort of improve the overall performance of the nonlinear convergence of these procedures, right? To simulate delamination, okay, what we do is we add a term like this to our overall formulation connecting all the plies, right? Delta here is a displacement jump, or what's known as a separation, okay, between the different plies, right? That defines a traction, an attraction-separation relationship that takes in the separation, right? It's multiplied by a stiffness tensor, which makes use of different stiffness values in the normal and tangential directions, and it's multiplied by 1 minus d cohesive, where d is a cohesive damage variable, okay? The damage variable is evolved according, as I said, mixed mode cohesive damage law. Okay. The key thing here is that the displacement jump or a separation and its variation that's needed, okay, makes use of a definition that respects the kinematics of the Kirchhoff shells here, right? And so we look at the two adjacent plies, right? We go to the mid-surface positions in the current configuration, right? Then we extend those to the boundary, right? Using the normal vector on each ply and half of the thickness, right? And then the difference between these two quantities gives me the displacement jump. Okay? Again, the key idea here is that your displacement jump respects the kinematics of the Kirchhoff shell. Now, one of the natural questions that the composites community always asks is when you start getting to the laminates that are thick. Okay, so each individual ply is very thin, right? There is no reason to say that there's a significant amount of transverse shear, but when you put all the plies together, you get a thick laminate, and of course, transverse shear plays an important role. And so, to understand what's going on, right, we basically build up a plate like this, okay, where we keep the thickness constant, okay, and then we use more and more layers, okay, to represent that plate, okay. And so with each definition, the layers get thinner and thinner and thinner, but their sum total is the same, okay. And then these layers are connected with the cohesive interfaces where the cohesive stiffness parameters can be computed to be consistent with the behavior of a solid. Okay, so in fact, you can directly compute the value of a cohesive stiffness by mimicking a pure shear condition, for example, right? And so then we take a point load, we put it in the middle of a plate like this, okay? And then you get a deformation like this, right? And so if you plot the vertical displacement from side to side, right, you get a curve that looks like this, okay? And here we're computing a solution that's consistent with the Reisner-Mindlin shell theory, okay, which takes transverse shear into account, right? And here is an isogeometric solution using 2 plies, 6 plies, and 12 plies, right? And so globally, the solutions are the same, right? But of course, something happens under the point load. And if you look at the Reisner-Mindlin solution, you can actually see localization here, right? Deformation under the point load. If you're only using 2 plies, you completely miss it, right? But as you increase the number of plies, and as a result, you increase the number of cohesive interfaces, you actually go and you match the Reisner-Mindlin solution at the end of the day, right? And so the conclusion is that while at the level of each lamina, there is no transverse shear. Once you put them together and put them together with cohesive interfaces, at the level of the laminate, you recover appropriate transverse shear behavior. Yep. Very good. And then finally, when it comes to impact and dynamic problems, right? Supposedly, you have, there's delamination between the 2 plies, right? So when the plies separate, you don't want to introduce any traction. You want them to separate freely, right? But then when the plies move toward each other, you don't want them to interpenetrate, okay? And so, of course, the natural choice is to use the cohesive stiffness in the normal direction, right, to preclude the non-interpenetration of the plies. And what happens in this case, right, is as you switch from opening to closing, right, the local stiffness changes, okay? And so when it comes to implicit procedures, these become very hard to converge because in the case when you have a highly dynamic event and the plies are chattering, you kind of go from opening to closing. Your stiffness changes locally and it kind of drives your Newton solvers crazy. And so what we did, we changed the constitutive behavior in the normal direction, right? By basically taking the original cohesive stiffness, right? Through a cohesive variable, we're letting it go to 0, right? So eventually the slope here becomes 0, but then we add a quadratic sort of penalty that's proportional to the amount of damage, right? That's been developed. Right, and you pick up a curve with sort of the 0 slope that comes into the that comes into the origin here, right? And so then as a result, right, it's when you have full delamination, d goes to 0, the linear term in the penalty drops, but the quadratic term in the penalty picks up and precludes the ply interpenetration. And so what it does, right, it again significantly improves the nonlinear convergence and the robustness in these calculations. Okay, so let me take you through some experimental validation. This is a flat panel impact. This is famous paper from Ravi Young, 2013. This is an 8-ply case. Here's a lamination sequence: 0 repeated twice, 45 repeated twice, negative 45 twice, 90 twice, symmetrized. Right, and so what we're doing, the plies with the same fiber orientation are grouped together. Okay? We're going to impact them on 2 different energy levels, 6.5 and 25 joules. Okay, the impact duration is about 3.5 milliseconds. Right, so here's a frame. Here's our composite panel. Right, here's the impactor. Okay. So here's the matrix damage. On top is for the higher energy impact. Bottom, lower energy impact. Okay. Here's a distribution of matrix plasticity, right? At different, right? And so you can see that while the magnitude is not very high of the effective plastic strain, right? You do see a fairly pronounced effect. Okay. Here we're looking at the 6 different interfaces, right? And these are delamination patterns, right? Basically contours of the cohesive damage, right? You see the typical peanut-shaped delaminations as you would observe in this case, although it is well known that interfaces toward the back tend to generate more delaminations, but we're not capturing it in this experiment. Here's a contact force history for the 6.5 case. Only the peak forces are given. We're matching those pretty well. For the 25 joule case, the duration of the impact is predicted very well, but there's some discrepancy in the peak force, probably having to do a lot with, again, boundary conditions and sort of the inability to generate enough delamination in the rear interfaces. Okay. Now, on this plot, right, I'm showing a history of the displacement. Right, we take a point of the top ply and the bottom ply directly under the impactor, and we plot the displacement at that point as a function of time. Okay, and so you can see the displacement ramps up, right, as the impactor drops down. At maximum displacement, the impactor turns around, right, it gets bounced off the structure. Okay, the displacement goes back to 0, right, but instead of going directly to 0, it oscillates against a non-zero value. Okay, and that non-zero value is exactly the size of the dent that was measured experimentally. Okay, so that's the plasticity effect, right? We're actually able to capture not just the force histories, but so forth. We're actually capturing the size of the dent, okay, because of the plastic formulation, right? And then the same thing for the 25 joule, right? Much higher displacements. Okay, they come back at the end of the impact and again oscillate around an experimentally measured 0.5 millimeter dent. Okay, on that plate. Okay, here's a different problem. 25 joule impact. In this case, a composite specimen has actually 24 plies. Right, this is starting to get quite expensive for sort of traditional finite element simulations. Right, and here we actually this is the impact tests were done at the University of California, San Diego, my former colleague, Hyun Kim, right? And then they're actually able to measure delaminations through some CT scanning, okay? And so here we're comparing the delamination patterns at 23 interfaces, okay? And comparing them to the CT scans, right? And what you see is that sort of the extent and the relative magnitudes in many instances compare quite well. Okay, so we're very happy with these results. You go to interface 11, 10, etc., all the way to the end. And again, we're not seeing as much delamination on the rear, on the very last, interfaces as we should. But you can see everywhere else, right? The agreement between what you see on a CT scan and what we predict in the calculation is quite good. Okay, here is a contact force history, and the matching is okay. No data on the dents were reported in this case, right? And so, final impact example I want to show you is a impact on a stiffened composite panel at 50 joules. Okay, and so you have the stiffener, right? You have the plate or the panel, you have the stiffener sitting on top, right? And the stiffener actually has 16 layers of CFRP, right? And the geometry is given here, right? So we're not just looking at a flat structure, right? We're looking at a curved structure. Okay? So the radii of curvature are given and are exactly represented through these spline or NURBS type functions, okay? So we have a full 16-layer model of the stiffener, right? But the plate itself is modeled basically a single Kirchhoff shell because we don't expect any significant delaminations there, right? So here's the view from the side, right? You can see the impactor that's descending on the stiffener. Okay, let me play this again, right? And you see the onset and growth of delaminations, right, between the different plies, right? In some cases, the extent of the delamination is quite large, right? But at some interfaces, you hardly see any. Okay, and again, that behavior, of course, depends on what fiber orientations are stacked on what fiber orientations and so forth, right? So here's another same movie playing again. Okay. Right. So here's a force time history, right? And now it's kind of remarkably captured quite well for this much more complicated case. And again, I suspect that the when it comes to impact on plates, the boundary conditions in the experiments are not very well characterized. Okay, so in this case, right, you can see all the action takes place away from the boundaries. Right? So because the problem is less sensitive, okay, we can actually capture the forces much better. Okay, and also their experimental colleagues reported indentation size. Okay, and looks like we're capturing that pretty well, also, which is very good. Okay. Here, our experimental colleagues are showing the extent of the delaminations, right, that they are able to sort of capture through CT scanning, right? And it's about 80 to 90 millimeters. In our calculations, we're getting almost 80 millimeters, right? So here, what we're doing is we're taking all of the contours of the cohesive damage variable, and we're plotting it on each interface, getting this sort of very nice kind of composite image, right? And you can see that the delaminations are curving very nicely around the curved interfaces. Okay. All right. So in the remaining few minutes, let me conclude with our more recent effort. Okay, and in the introduction, it was mentioned that I'm a co-director, or actually a director of Mechanics of Undersea Science and Engineering Center, and sort of one of the central undersea problems is how undersea vehicles and platforms respond to undersea explosions or blast, okay, underwater explosions, what the community calls UNDEX, okay. And there's also an interest in going in the direction of composite materials, especially for unmanned undersea vehicles. So the US Navy is interested more and more as to how composite materials, structures made of composite materials, respond to extreme events like this. And so we started to develop a framework. It's a fully coupled fluid structure interaction framework. It's a sort of a presentation itself. Certainly there's no time to go into details. I just wanted to focus on the composite side, right? But it's a fairly complicated problem where you have to model a multi-phase fluid, okay? And in this case, you have to keep track of water, explosive gas products, air, okay? We want to be flexible, want to be able to handle a variety of structures. Okay, in this case, I'm going to show you some results using the multi-layer isogeometric Kirchhoff shell, okay, theory, but we do other things. And the challenge is that you have many interfaces in this problem, okay? You need to keep track of the interfaces between fluid and structure. We're using an immersed approach. You have an interface between water and explosive products, where this is done through a level set technique. Oftentimes, the structures are air-backed, okay? So you also need a formulation for air and how that interacts with the rest of the system, right? And in these multi-layer structures, as I showed you, you have to keep track of structure interaction, and this is done through cohesive interfaces, right? We have very good collaborators, again, just down the road from Brown University, 30-40 minutes. At the University of Rhode Island, a group of Arun Shukla is doing really cutting-edge experiments on undersea explosions using a water tank facility that they designed in their lab, okay? And so here's what a calculation of this is a composite plate, right? This is a quarter of the domain, volumetric domain that's filled with water. There is a charge here, right? These are not sort of full scale, these are lab scale experiments, right? So the standoff is, 76 millimeters, right? Which is what, even less than 10 centimeters, right? So these are fairly small structures. And so here's the calculation, right? We're setting off a charge, right? You see this very fast shock wave that goes through water, impacts the structure, which becomes very dynamic, right? And then you see a very slow growth of the explosive bubble, okay? And that explosive bubble continues to interact and deform the structure, right? And then the process continues because that bubble collapses and then it re-expands again. And so you have this very wide range of timescales, okay, that you need to track in the problem, right? The water shock, the shock in water travels on the order of microseconds, okay? While the expansion and the collapse of the bubble is milliseconds, right? So there's 10 to the 3, 10 to the 4, orders of magnitude of time scales that you need to handle. This is the biggest challenge in these calculations, okay? That's a standoff at twice the distance, 155 millimeters, right? Again, you can see that the fluid mechanics, the explosive bubble, and the structure interacting in a very dynamic way, okay? So that plate, composite plate, actually had 4 layers, okay? So 4 that are shown here, and 3 cohesive interfaces, right? And what I'll show you is a movie, okay, that shows the time history of cohesive damage here, right? And fiber damage with a 76 millimeter standoff. And what you see is that cohesive damage occurs first, okay? Then the different lamina are starting to basically act in an independent fashion. They can't support as much load, and you start seeing the formation of fiber fractures here, right? These are plus minus 45 plates, and you can actually see that pattern of plus minus 45 fiber fractures. This is 152 millimeter standoff. Again, delamination starts from the corners. Okay, once enough delamination happens, then the fractures start. Okay, so that's a behavior that our experimental group is observing, but it's kind of hard to do this with optical type techniques underwater. And so our high fidelity FSI tools with composite damage is actually able to capture this. Okay. Here's some experimental validation, right? The maximum size of the explosive bubble is recorded to be about 100 millimeters, and we're seeing that in the calculations, right? Our experimental colleagues had a DIC system set up where they're tracking the displacement of the center point of the composite plate, and we're doing very well at the early stages, right? And then we undershoot. Okay, this can be due to multiple factors, right? If we choose the right value of the compressive strength, we can actually induce the fiber fractures I'm talking about. Once you induce the fiber fractures, you can have the second sort of burst of the displacement here, right? So the only way to capture it is by inducing fractures. And if we look at the predicted size of the cracks in the calculations and in the experiments, about 30 millimeters. So we're quite happy about that. Okay. All right. So 45 minutes, as I was told. I want to thank you, everyone, for your attention. This work was supported primarily using funding from Office of Naval Research. It was very helpful in starting the Mechanics of Undersea Center. And let's go to questions. And I also sort of put a list of papers that were recently published on the subjects that are presented as a part of this presentation. So let me stop here and take questions.
so much, Professor Yuri, for such an insightful and thought-provoking keynote on isogeometric analysis, breakthroughs in computational mechanics of laminated composites and beyond. Your expertise and innovative perspectives have truly enriched our understanding of this critical area in material science. Now we would like to open the floor for questions. Audience may kindly post the questions in the chat box so we can address them one by one. Sir, there is a question from Nivedita. How does the proposed isogeometric analysis-based framework improve computational efficiency and accuracy compared to traditional finite element methods in modeling damage in CFRP structures?
Okay, this is an excellent question. If you see what happens in finite elements, right? So again, if you want to be able to predict damage on every ply, right, and delamination, kind of you go in the direction of a multi-layer theory and its discretization. Okay, so in traditional finite elements, what do you do for every individual layer? Okay, you have two choices, right? You either would use a solid element, okay, or you would use a solid-like shell. Okay, they're very similar. Okay, these are typically low-order elements. In order to get good performance of low-order elements, right, then the size of your in-plane element has to be comparable or very similar to the thickness, right, of the individual ply. Okay, and so if you're looking at something that is, let's say 10 by 10 or 20 by 20 millimeters, right, the size of individual ply is a fraction of a millimeter. So you can do the math, right, and you end up with about 100 by 100 or 200 by 200 discretization on each individual, right, ply. And then you would want to go and do 16 plies or 24 plies. You can see that the degrees of freedom explode completely, right? And then, trying to do this at the structural level is out of reach. Okay. What isogeometric shell approach allows you to do, right, is first of all, you can afford to use much larger in-plane elements for a couple of reasons. One, Kirchhoff theory doesn't have an issue with transverse shear, okay? And so you can reduce the number of degrees of freedom in plane significantly, right? And also, you only have 3 displacements per node, right? So for example, if you were to use a solid element, you would have to, for every layer, right, you'd have to repeat, right? There's 1 displacement on top, 1 displacement on the bottom, so that doubles. See what I mean? And so you can dramatically reduce the number of degrees of freedom and still get the accuracy, right? And so, in some of the examples with the laminates, okay, a commercial code would run for a week, okay, while we could produce results that are, qualitatively the same or even better, right, on a much smaller mesh with an overnight type calculation. I think this is where the opportunities are. I hope that answers your question.
Question from Sharad Clear. How does material properties of the composite plate, such as anisotropy and layering, influence the shock wave propagation and energy dissipation during
index? Well, I think this deserves a separate study. Okay, we were able to get to the point where we can, couple complex multi-phase compressible flow with these multi-layer structures. The structure is still relatively thin in the thickness direction, even for the multi-layer case, relative to its overall size, okay? And so we're probably not very accurate at tracking shocks through the thickness of the structure, okay? However, it appears that we're able to capture delaminations and fractures very well, okay? And so, so looks like if you want to see if you have any sort of residual life left in your undersea sort of vehicle, right, we should be able to kind of do the calculations at least at the component level and sort of predict how badly damaged the structure is, right? Tracking shockwave propagation through the thickness would require a much different approach to these problems.
We have one more question, Professor. What are the key challenges encountered in implementing the mixed mode cohesive damage model for delamination? Question from Gopika.
I think the biggest challenge was to get the opening and closing under control, right? When your cohesive damage variable is nearly 1, okay? So once locally you have complete delamination, right? Yet you don't want to, right, when the closure happens, right, you don't want interpenetration. I think developing that modified law that basically uses a continuous stiffness, right, as you transition from opening to closing. And it took us a while to understand where a lot of the problems were coming from, right? And that was it. I think once we've done that, okay, then the calculations were going, a lot more smoothly with a lot less, nonlinear divergence. Another thing that is helpful is the use of viscous regularization, okay, where you sort of lag the damage a little bit, okay. It also helps overall with the nonlinear procedures.
Any more questions? Once again, thank you so much, Professor Yuri, for being with us here today. And thank you to everyone who joined us for the session. Have a good day. We'll soon have our next keynote session by Dr. Kalapa Prashanta on the topic thermomechanical behavior of 3D printed shape memory polymer nanocomposites at 12 p.m. Thank you.
Okay.
Thank
you very much.
Just
Thank you,
maybe we
Professor.
have another technical session at 10:30. Yeah.
Okay.
Thank you. I request all the candidates to join 10:30. Thank you, Professor Yuri. See you.
Thank you very much. I think it's midnight here, so I think I need to
Okay.
need to go.
Good sleep.
But again, thank you again. I appreciate the invitation.
So our next technical session going to begin at 10:30. So I request all the candidates. I think the next slot going to present in the next slot. Request to be here. You can check your presentations, share your presentation. You can try. We will sharply start the presentation at 10:30. So very good morning, Dr. Siko. I can see you here.
Hello. Yeah, Dr. Praveen.
Yeah, we can start the session within 6 minutes.
Yeah, perfect.
Thank you.